We're embarking on a super high-energy, totally mind-expanding journey into a subject you probably think you already know inside and out. We are exploring the 30,000-year skyscraper of mathematics. And look, trust me on this, it is entirely different from the rigid, boring subject you might remember from middle school.
Every math rule was once a crazy invention. I really want you to absorb that for a second, because it completely reframes everything we're about to talk about. Math just isn't some stale set of natural laws that we are all forced to memorize. Actually, scratch that. It's more like a wild, messy saga of rebellious human inventions. Every single symbol, every rule, every concept we use today, at one point it was considered a crazy idea, a strict taboo, or even complete nonsense by the people of its time.
And this saga covers a truly massive scope. Our journey stretches all the way from primitive bone marks 30,000 years ago, over to the strict logic of Euclid around 300 BC, tearing through the invention of algebra in the 9th century, diving into the mind-bending calculus of the 1600s, and zooming all the way to 1936, when the Turing machine changed our world absolutely forever. Okay, let's dive right into this. Here is our agenda. We're going to start with the origin of the numbers, then explore logic, zero, and algebra. After that, we'll hit the European math revolution, followed by breaking the mathematical limits, before finally wrapping up with how math becomes a machine.
All right, let's walk into floor number 1, origin of the numbers.
This right here is where human beings first turned physical reality into an abstract concept. Just think about the sheer age of these artifacts. Over in the Czech Republic, archaeologists dug up wolf bones with tally marks carved into them that are 30,000 years old. In Africa, we've got the 20,000-year-old Ishango bone showing grouped markings. Now, I know it sounds incredibly simple to us today, but this represents literally the single most massive leap in human cognition. Why? Because for the first time ever, humans separated the quantity from the physical object itself. Before this, 3 sheep were simply 3 physical sheep standing in a field. But once you start etching marks into bones, 3 sheep, 3 days, or 3 moons can all be perfectly represented by the exact same abstract concept, 3 marks. And just like that, mathematics was born. Let's jump forward a bit to about 5,000 years ago in Mesopotamia. The Sumerians came along and gave us this incredibly important number, 60. They invented one of the first systems of numerical symbols, and they built the whole thing entirely around a base 60 counting system. Now, they didn't just pull 60 out of a hat. They chose it simply because it's so wonderfully divisible. You can cleanly divide 60 by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. It's like a math cheat code. It made dividing up land, crops, and most importantly, time, incredibly efficient. And what you should really take away from this is how this ancient history connects directly to you right now. This brilliant Sumerian and Babylonian invention isn't just stuck in a dusty textbook. It's quite literally ticking on your watch right this second. It is the exact reason we have 60 seconds in a minute, 60 minutes in an hour, and 360 degrees, which is, you guessed it, simply 6 times 60, in a full circle. Every single time you check the time, you are relying on a 5,000-year-old piece of math.
Moving on up to floor number 2, logic, zero, and algebra.
So we really have to talk about a massive paradigm shift that happened around 300 BC. On one side, you had the Egyptians and Babylonians. Look, they were master builders. They built the pyramids, obviously. But their math was essentially a practical handbook. They knew their formulas worked because they got the right results, but they didn't really bother asking why they worked. Into the Greeks, and specifically a guy named Euclid. Euclid completely reinvented the game. Instead of a handbook of approximations, he built a rigorous, logical system based entirely on foundational axioms and definitive proofs. For the Greeks, once you proved a theorem using strict logic, it was undeniably true forever. Yet, even with all that incredible Greek and Roman logic, they were missing something that seems so incredibly obvious to us: the number 0. I mean, just imagine the absolute nightmare of trying to do complex multiplication using Roman numerals. They have no columns and no place values. It's a mess. Crucially, in 628 AD, an Indian mathematician named Brahmagupta revolutionized calculation. He was the very first person in history to define 0 not merely as an empty placeholder, but as a fully independent actual number that you could add, subtract, and multiply just like any other. This was a real game changer. Let's see how this builds a couple of centuries later over in Baghdad. In 820 AD, a brilliant mathematician named Al-Khwarizmi took these concepts and invented algebra. His major breakthrough was using a symbol to represent an unknown quantity, which allowed mathematicians to set up and solve universal equations. So yeah, that frustrating task of finding x in middle school, you can trace that directly back to him. He gave us a universal, step-by-step procedure for solving problems, and his Latinized name, Algorithmi, actually gave the modern world the word algorithm.
Up next, floor number 3, the European Math Revolution.
As these Eastern concepts started bleeding into Europe, they triggered a chaotic era where radical new ideas met some really intense pushback. You can clearly see this messy human element in a legal decree from 1299. The powerful city of Florence actually banned the use of Arabic numerals in commercial bookkeeping. Now, why on earth would they ban a vastly superior system? Well, because the idea of an easy-to-change zero completely terrified merchants. They were convinced that with a quick stroke of a pen, a fraudster could add a tiny zero to the end of a ledger and just magically turn a 10 into a 100. It actually took a surprisingly long time for Europe to overcome this fear and fully embrace the system.
But once the 16th century rolled around, mathematicians just started breaking the rules with absolute audacity. You had Girolamo Cardano solving complex equations and repeatedly hitting a brick wall with impossible concepts like negative values and square roots of negative numbers. But instead of giving up, Cardano just boldly used them anyway as temporary tools to reach the final answer. And right around the same time, an engineer named Simon Stevin looked at the absolute nightmare of calculating with fractions like 5/12 and decided to simply replace them with infinite decimals. He totally smoothed out the mathematical landscape, changing commerce and science forever.
And this leads us to one of the greatest unifications in human history. For literally 1,500 years, the Greek tradition of geometry, which was all about shapes and lines, and the Arabic tradition of algebra, which was all about equations, were completely separate languages. They didn't talk to each other. But in 1637, René Descartes bridged that massive gap. By inventing the coordinate system, he proved that every visual shape can become an equation, and every equation can become a visual shape.
Descartes' new analytical geometry set the perfect stage for Isaac Newton and Gottfried Leibniz to invent calculus in the late 1600s. They were tackling two very extreme problems. The derivative was all about calculating instant speed at a specific, frozen moment in time. The integral, on the other hand, was about calculating an area by summing up an infinite number of infinitesimally small pieces. Newton and Leibniz proved that these two mind-bending, seemingly unrelated concepts are actually exact opposites of each other. This single breakthrough became the operating system for literally all of modern physics.
All right, floor number 4, breaking the mathematical limits.
As we step into the 19th and 20th centuries, the whole tone becomes deeply philosophical, and foundational rules are totally shattered. Remember Euclid's absolute logic from earlier? Well, for 2,000 years, everyone just accepted his axiom that through a single point, you can only draw exactly one parallel line. But in 1829, Nikolai Lobachevsky came along and broke that rule completely. He proved that if you assume a space isn't flat, but curved, kind of like a horse saddle, you can actually have infinite parallel lines that never intersect. He revealed that mathematical axioms aren't unquestionable truths of the universe. They're choices. If you choose different axioms, you can literally create entirely new, curved mathematical universes.
So math was no longer just about describing our immediate reality, it was about exploring the very edges of logic itself. George Cantor took this to the extreme by looking into infinity. We usually think of infinity as just one giant concept, right? But through his highly controversial diagonal argument in 1891, Cantor proved that infinities are not a single size. No way. He demonstrated mathematically that the infinity of real decimals is vastly, undeniably larger than the infinity of whole numbers. Some infinities are literally bigger than other infinities.
Then Bertrand Russell came along and nearly destroyed the entire foundation of set theory with just a single question. He asked, does a set containing all sets that don't contain themselves contain itself? If your brain just threw an error 404 screen, don't worry, you are exactly where the world's top mathematicians were in 1901. If the set contains itself, it breaks its own rule. If it doesn't contain itself, it must be included in the set, thus breaking the rule. This tiny little paradox forced mathematicians to tear down and painstakingly rebuild the very foundations of their logic.
And all of this philosophical turmoil led to the ultimate climax in 1931. Kurt Gödel published his Incompleteness theorem, dropping an absolute bombshell on the entire mathematical community. He proved that within any mathematical system, there will always be true statements that cannot be proven by the system itself. Basically, he showed that a mathematical system can never be entirely complete and perfectly consistent at the exact same time. That 2,300-year-old Greek dream of a perfectly proven, absolutely airtight mathematical system, Gödel proved it was a literal impossibility.
Finally, we reach floor number 5. Math becomes a machine.
This is the era where abstract mathematical thought finally escapes the human mind and enters the physical world. In 1936, an English mathematician named Alan Turing created a conceptual model called the Turing machine. At first, it was just an abstract definition of what it actually meant to compute something. But very quickly, engineers realized this pure mathematical concept could be built out of wires, vacuum tubes, and eventually silicon. Math literally escaped the mind and got a physical body. Turing's abstract logic is the exact foundation that powered wartime codebreakers, and it's the exact same logic powering the modern AI smartphones sitting in our pockets today. The very screen you're using to watch this explainer right now is a materialized Turing machine.
So, as we wrap up this explainer, I want to leave you with a final provocative thought. We've seen math evolve from scratches on a 30,000-year-old bone to machines that can simulate reality. But this massive skyscraper, it is still heavily under construction. There are ancient problems yet unsolved, and entirely new branches of mathematics being invented right this second. So, what do you think is the next mathematical invention? The next concept that sounds like impossible nonsense today might just be the exact tool that tomorrow's generation uses to completely rewrite our understanding of the universe. Keep that curiosity alive, and thank you so much for exploring with me.
If you enjoy this video, please like, share, subscribe and hit the bell to the latest update from my channel. Thank you for watching till the end, and see you in the next video.